So among all pairs of numbers whose sum is 16, find a pair whose product is as large as possible. What is the maximum product? Okay, now, I do want to point something out. You can do this by inspection fairly easily. I will do it the long way, but feel free to do this by inspection. So basically they're saying, let's say I have an unknown x and an unknown y, and I add them together, I get a 16. What that would mean is, let's say I want to solve for y. Okay, so I minus x, cancel, cancel, and then what that would give me is y is equal to 16 minus x. So we know, basically, we want to know the product, right? So the product is x times y, and we want a maximum, max that thing out, right? Okay, which the maximum is going to be the vertex. So we know that's the vertex. So if it's a negative parabola, that would actually be the maximum, would be the vertex, right? So we can figure this out. Okay, cool. All right, so what I'm going to do is I'm going to do substitution. So right here, I said, well, y, x is just equal to x, but I'm saying y is equal to 16 minus x, so I can plug it in. I'm not necessarily recommending you do it this way, by the way. Inspection is probably way easier. I will be showing you that in a second. But I'll show you the concept of how to do this using parabolas and whatnot. But I'll show you an easier way in a second. Okay, so we say x times 16 gives me 16x. And then I say x times negative x, which gives me negative x squared. Okay, now I'm going to flip the order. So I have negative x squared plus 16x. Now, what that would mean is the coefficient of the x squared, or the a, is going to be a negative 1, right? Implied or understood negative 1, right? And then the b is going to be the coefficient of your x, which is a 16. And we already went over, well, the vertex is equal to negative b over 2a. And again, if you don't want to do it this way, I would understand. Okay, so negative b in this case is a negative 16. And we have 2 times a, which is a negative 1, which gives me negative 16 over negative 2, which gives me positive 8. Okay, so we know x, the x value of the vertex, let me get a little space there. The x value of the vertex is equal to a positive 8, right? And that's we're dealing with the vertex here, right? That's what we're trying to find out. Which means now we plug it in, that 8, and it gives me the y value. Okay? So, for instance, we know y is equal to 16 minus x, where x is equal to 8, which means y is equal to 8. So we have x is equal to 8, right? X is equal to 8 right there, and we have y is equal to 8. And that works. We found it out. Among all pairs of numbers whose sum is 16, find a pair whose product is as large as possible. What is the maximum product? Okay, now they also want to know the maximum product. Well, that's just x times y. Well, what is x times y? That's 8 times 8, which gives me a 64. So that's the max. Max product. Okay, now, what about inspection? Okay, well, 2 numbers. We could, I can make a little chart, x, y. That could be 1. That would be 15. That would be 2. That would be 14. That would be 3. That would be 13. That would be 4. That would be 12. That would be 5. That would be 11. That would be 6. That would be 10. That would be 7. That would be 9. Oops, 9. And that would be 8. And this would be 8. Okay, so if we did all these products, right, we multiply all these together, products, we could just do it by inspection. These are all the combinations of numbers that the sum of which is 16. Now, technically, this would wrap back around, and you'd end up with, what about x is equal to 15? Yeah, but the product is the same whether it be 1 times 15 or 15 times 1. So there's no reason to keep going. So if it occurred to you, technically, this should keep going, and you'd end up with like a 9 and a 7. You are technically correct, but there's no reason to do this because it's going to give you the same result. 9 times 7 is the same result as 7 times 9. So you can stop at this point. You don't have to keep going. But if it did occur to you, you're not wrong. There are more combinations possible. They're just repeats, though. Okay. Having said that, we say 1 times 15 is 15. 2 times 14 is 28. 3 times 13 is 39. 4 times 12 is 48. 5 times 11 is 55. 6 times 10 is 60. 7 times 9 is 63. 8 times 8 is 64. Oh, that's a 4, believe it or not. Okay. And that's it. We got it. Same result, right? So that's probably way easier to do it by inspection. But again, I wanted to show you the more complicated mathematical way of doing it with that. But again, just do it by inspection. That's fine. There's a couple of other word problems like that you can do by inspection instead. And that's always, sometimes that's really a good option. Unless they tell you specifically how to solve a problem, in which case you don't have that kind of flexibility. You need to solve the problem the way they told you to solve that problem. But if they don't specify, generally speaking, you're free to solve it by inspection or other means. So that's okay. All right, so using the leading coefficient test to determine the end behavior of a graph of the given polynomial function. Okay, now before we get started, I just want to point out a couple of graphs here. So let's say we have a function, and it's a cube, okay? Now, it's going to look something like this. This is me doing it freehand, so it's not great, but it looks something like that, right? Now, I want to point something out. Well, let me do two, and then I'll point out what I want to point out. So that's the positive one. It starts low, ends up high. It's an odd one, though. That's a 3, okay? Just want to emphasize that. Well, what happens if, instead of being positive, it's negative? Well, it's the same one, but I'm going to flip it, right? So now it's going to look more like this. It's meant to be more curvy than that. I'm just not drawing very well right now. Okay, so instead of it starting low and ending high, now it's going to start high on the left, right? Going up to the left, down to the right. Okay, so that makes sense. So far, so good. Oh. Now I want to point something out. This pattern persists for all odd exponents, right? The same pattern of it being up and down or up, right? It persists, right? So for instance, let's say I had y is equal to x. Well, what's that? From left to right, left goes down, right goes up, right? Which was the same for a third power, right? Well, what about if it was negative? Well, a rough graph of that would be down, right? See my point? So from the left it's going up, and to the right is going down. It's reversed, right? And the same thing would even be true if I had a fifth power. The fifth power would look just like the third power, but it would be a little thinner, a little more stretched out along the y-axis, right? The point being is you only need to memorize this pattern once, and then you can generalize it to all the odd exponents, leading coefficient, the exponents. Okay, now let's look at what happens if we have even ones, right? So let's do a couple of examples. Though. Say we have f of x is equal to x squared, right? Well, that is going to look something like this. Okay, so they both face the same direction when it's even. They're going to be matching. And in this case, when it's positive, they're both up. Okay, well, what happens if it's negative? Well, it's the same thing, but now it's going to be going down and down. It's a very rough draft, but or drawing, but that's the point of it. Now, this is going to repeat if it's higher powers, though, right? So if I say f of x is equal to a positive x to the fourth, it's the same graph as the one above, but it's skinnier. A little flatter on the bottom and skinnier, right? So it's just a skinnier version of the one I had on the second power, right? Sixth power would be even skinnier, be stretched out even more along the y-axis. Eighth power would be even skinnier, be stretched out even more along the y-axis, make it look skinnier and taller, right? So the point I'm trying to make here is you don't need to memorize that many. You just need to memorize a couple of the positive and negatives. So there's only 4 different possibilities, right? So if you can memorize these 4 different possibilities, you can figure these out. Okay. So let's interpret these. So using the leading coefficient test to determine the end behavior of the graph of the given polynomial. Okay, so the leading coefficient. Okay, so this is positive, right? So positive, well, tiv. Right, so that's positive, right? And then 3, it's odd. It's odd. So what does that mean? It's positive odd. That means it's going to look like, right? It's going to look like this. It's going to look like this up here, right? Positive and odd. It's going to look like that over there. What that means is left to the left is down, right? Down. And to the right, it's up. That's what that means, right? Okay, let's look at the next one. Now, in this case, it is negative. Okay? And it's even. Okay? So they're both going to be facing the same direction because it's even, and because it's negative, they're both going to go down. So we're going to be using this version over here, right? This version over here, same thing, right? That's the one we use, right? Because it's an even and it's negative. Okay, excellent. So what does that mean? Well, just looking at the picture, it means they're both down, right? So I'll put both down. both down. If they make you specify, obviously you just say, left down and right down, or just both down.